All right. So question 3 is where this one gets a little bit more interesting. Um, Now we have two ropes, two strings, and they also happen to be going at angles. So that's going to build in and give us one of our formulas we have on the formula sheet. If you've peeked at that already, you may have seen some interesting looking stuff, and part of that was reserved for this question. So the tension in the lines, and I'm just going to put T because it's assumed to be the same in each, as long as everything's symmetrical and same angle. Part of this is going to look the same, right? So if we convert stuff around, fix units, again, we're trying to get to newtons, and grams aren't really great for that. Eventually, what we're trying to do is get mass times gravity for the weight hanging down from the block. That's what has to be supported if this thing's hanging in the air. But some extra things are going to happen here. We're going to have a 2 on the bottom of this to show that the mass gets cut in half, supported equally from the two ropes. And then we're also going to have an additional factor built in with the sine of the angle. So you may remember from previous problem set when we were dealing with vertical components and how our trig functions would help us to differentiate these and split them up. This gets built in. If you're in the lab section of the course, you'll see this later. Um, we'll even build this. We'll hang a block from two strings and we'll measure and we'll see that it works. Okay, so from here, we have a few different ways to approach this question. Just to spice things up and show you how things can be a little bit different, I'm going to go ahead and convert this from grams to kilograms just in the question, right? So remember, it takes 1,000 grams to be 1 kilogram, and I'm sorry, that's probably pretty small, but it's just moving the decimal around, something I'm sure you've seen before. This turns into 0.61107 and then kilograms. All right, and then once that's done, we actually have everything we need to plug in and finish the question. So I'm going to bring this over where I've got room to spare. The mass is that converted number 0.61107. Gravity, again, assuming Earth is 9.8 meters per second squared. On the bottom, you've got to be careful here because if you try to type this in the calculator all at once, what'll probably happen is it will divide by 2 properly, but then in a later step, not in the same one, do the sine function. So in this question and a few other ones that are similar, I would recommend working out numerator and denominator as separate parts, and then at the end, putting those together to resolve the answer. All right, but here our theta, remember, is the Greek letter talking about angles. That's 55.97. As mentioned, to avoid some of the issues that can pop up from calculator stuff, you can type this in all at once. You may have to run backwards, use additional parentheses. I'm just going to do these as separate parts. I think that's simpler for most people, depending on what device you're using. All right, but multiplying on the top, kilograms and meters per second squared will give us newtons. Multiplying those numbers, 5.988486 apparently. Then on the bottom, again, depending on your calculator, you may have to do this differently. Maybe you find sine of the angle first and then double it. Maybe you can type it straight on in, whatever. But that should give you on the bottom 1.657489, and it just goes on and on. No units on that. That's just a squiggly for numbers that keep going. Okay, so then with that scratch work out of the way, we've simplified down. We've gotten most of the work done for our answer. Now we just want to do the final part to evaluate. So taking and dividing these numbers will give us 3.61.